All right, let's look at one more example of conservation of energy in action, and this time we're going to throw in another spring because we always really love the springs. So I have a 0.450 kilogram object. It's at rest and it's attached to the end of a horizontal spring with a spring constant of 19 newtons per meter, and it's displaced 0.200 meters. So the spring is released, and then we want to find the speed of the mass when the displacement is 0.155 meters. I guess I should probably say the mass is released, not necessarily the spring. So here's kind of a setup of what's going on. Again, let me make a little sketch here. So this is what we got going on. Here is our mass. So our mass here, so this spring is going to be stretched out by about 0.200 meters. Now, by stretching it out, we have stored elastic potential energy. So this thing is going to want to go. Now, at some time later, we let it go. This thing is going to want to move back to equilibrium. So at some time later, here's our box, and then our spring is only going to be stretched by 0.155 meters. What we'd like to do is we would like to find the speed at this point. So once again, we can set up conservation of energy. So when it's fully stretched, I'll call that A. When it's at this point, 155 meters, we'll call that B. So my total energy at A has to equal my total energy at B. So I have my kinetic plus my potential at A equals my kinetic plus my potential at B. Now, for this thing here, because it's on a flat surface and there's no change in vertical height, I don't actually have to worry about gravitational potential energy. So I could say, because I'm going to set, I'm going to set this as my reference height of 0. So I could just say that E gravitational potential equals 0 for the whole thing. So when I'm dealing with potential energy, we're actually dealing with elastic potential. Now the other thing to simplify this is the object's at rest to start. When it's at A, we're holding it still. What that means is that the kinetic energy at this point is going to be 0. So we're going to eliminate that. So my potential energy at A is going to be half K times the stretching at position A squared. That's the energy that I'm starting with. Now this thing is going to move. It's going to have kinetic energy, this half mvb squared. And then we're going to have this potential energy because the spring is still stretched at this point. So we're going to have this half kbx squared. Now, we can't get rid of mass, nor can we get rid of k, because we don't have a mass in every term and we don't have a k in every term. But we do have a half in every term, so we can get rid of all the halves. So half, half, half. So I have kxa squared. This is going to be mvb squared plus kxb squared. My interest in this problem is to find the speed. So before we get to that, let's bring this kxb squared to the other side. So we know that mvb squared is going to be this kxa squared minus kxb squared. We can divide both sides by m, divide both sides by m, divide the whole thing by m. And then we have vb squared equals this mess, or vb is going to be the square root of kxa squared minus kxb squared divided by the mass. So let's plug in what we know. So we have a spring constant of 19 newtons per meter. We have that stretching at position A. We have a stretch of 0.200 meters. Don't forget your square. And then we have that 19 newtons per meter again. This time a stretching of 0.155 meters. Once again, don't forget the square. And then the last thing, we have this mass of 0.450 kilograms. So a lot of work going into this to set this up. But, take it slow and steady. Don't rush these problems. There's no incentive for you to rush. Take it slow, steady, methodical, all those buzzwords that I can throw in there. All right, so if I do this really carefully, what I am going to get for a speed. Now, I just want to check my answer one more time just because it seems a little small, but let me double check just in case. There's never any harm in double checking your answers. I tell myself that. I tell my students that. Sometimes they don't listen to me, but it is what it is. All right, yeah, I guess I'm going to be happy with this. All right, so my final answer for this, for the speed, I'm going to get a speed of about 0.2821 meters per second. So with this object, when it's let go, when it gets to this point here, it's going to have a speed of about 0.821 meters per second. So we've gone through a few examples of conservation of energy with just regular systems. The next thing we're going to look at is the simple pendulum, which you would have looked at in Science 10, but we'll get to that in another video.